All right, let's talk about something really cool. How do you take an AI, a chatbot, and turn it into a real apprentice? I'm talking about an AI that can actually think for itself, do research, and solve problems without you holding its hand. Well, Salesforce AI just dropped a paper on exactly this, and their method is, honestly, it's brilliant.
Yeah, this is really the heart of the matter, right? We're all used to LLMs that just do what we tell them. But teaching one to plan, to decide what to do next on its own, that's a completely different level of challenge. It's a whole new ballgame. So, there are basically two ways you can go about this. First, you've got the multi-agent system. Think of it like a whole team of AIs, an assembly line where one agent plans, another one searches, another one codes. It's very structured. The other way, the autonomous single agent. This is more like a lone apprentice, a single AI that has to learn all the skills and figure out what to do and when. In this paper, they're betting big on the apprentice. Let's see how they did it.
Okay, so first things first. To train our apprentice, we got to give it a toolkit. But here's the clever part. They kept it super simple. The idea was to force the AI to get smart, not just rely on fancy tools.
And when I say simple, I mean really simple. Just 3 tools. 1, a basic internet search. 2, a tool to read a web page. And get this, it can't even click links on the page. It has to go back and search again if it needs to dig deeper. And 3, a simple code interpreter for doing calculations. That's it. By making the tools so basic, the agent can't just brute force a solution. It's forced to learn an actual strategy.
All right, so it's not just about the tools, right? It's about how the agent uses them. The workflow is the other half of the puzzle, and the way they set this up is super important for keeping the AI on track. Check this out. This workflow diagram shows off a really clever trick. See, LLMs can get lost in long conversations. So instead of a messy chat history, the researchers packaged everything, the main question, what tool the AI just used, and the result it got, into a brand new, single prompt for the very next step. It's like turning a giant, confusing marathon into a series of short, manageable sprints, and models are way, way better at that.
But what happens when even those sprints start adding up and the context window gets full? Well, they gave the agent another tool. It's called clean memory. Basically, the AI can decide for itself, okay, this is getting too long, and then it stops, summarizes the most important stuff it's found so far, and uses that summary as its new memory. It's literally teaching itself to take notes. That's another huge step towards real autonomy. So we've got the tools, we've got the workflow, but now for the real magic, the secret sauce. How do you actually teach the apprentice to be good at this? This is where we get into the heart of the paper, their special reinforcement learning recipe.
Okay, quick refresher for anyone who needs it. Reinforcement learning, or RL, is basically how you teach an AI through trial and error. The agent tries something, and if it does well, it gets a reward, like a treat. If it does poorly, no treat. You do this thousands and thousands of times, and eventually, it learns what actions lead to the best rewards.
But, and this is a huge but, there's a classic trap with this method. What if the agent learns the wrong lesson? What if it thinks, hey, the more actions I take, the more chances I have to get a reward? It could end up just taking a bunch of useless steps, thinking that being busy is the same as being smart.
And that's exactly what happened when they tried a standard approach. Look at this graph. The red line shows that the agent just started making more and more and more tool calls. I mean, it's going off the charts. But its actual performance, it completely tanks. It was learning to spin its wheels, not to solve the problem.
So the solution is something called length-normalized advantage. And the idea is actually super elegant. They take the reward the agent gets, and they divide it by the number of steps it took. So think about it. A short, clever solution gets a massive reward. A long, meandering solution, even if it gets the right answer in the end, gets a tiny reward. This directly teaches the agent that efficiency is king.
And that's the core of their 3-step recipe. Step 1, those length-normalized rewards to make it value efficiency. Step 2 is trajectory filtering, which is a fancy way of saying they just threw out all the bad training runs. The ones that had errors or just spat out gibberish. And step 3, partial rollouts. This is cool. If an agent got part of a problem right before messing up, they'd save that good part and let other attempts learn from that point forward. Really smart stuff.
Okay, so that's the whole training method. It sounds amazing on paper, but the big question is, did it actually work? Did our apprentice graduate? Let's look at the results.
The big number is 28.7%.
Now, I know what you're thinking, that doesn't sound very high. But this score is on a test called Humanity's Last Exam, which is designed to be incredibly difficult. For a model this size, getting a 28.7% is actually a huge deal. It's a state-of-the-art result.
And just to put that into perspective, look at this. Before the training, the base model was stuck down at 17.3%. This training recipe rocketed it up to 28.7%. That's a 65% relative improvement. It even beat out a major proprietary system from OpenAI on this same test. That is a massive, massive jump, all thanks to that clever training.
But this next part is what I find really fascinating. The agent didn't just learn to use its tools more often, which you can see on the left. It actually learned to think more efficiently. The chart on the right shows that the length of its internal reasoning, its thought process, actually went down by almost 30%. So it's using tools more, but thinking less to get to the answer. That's a sign of real intelligence, not just brute force.
Whew, okay, that was some seriously complex stuff. If your brain is kind of smoking right now, don't worry, that's totally normal. But if you actually enjoyed that feeling and want more deep dives just like this,
then you should probably go ahead and subscribe to VibeDoc. We promise it only hurts a little. All right, let's wrap this up with the big takeaways.
All right, time for the takeaway. What does all this research really mean? First, and this is huge, they've shown that a pretty compact RL recipe using synthetic data can turn a standard reasoning LLM into a seriously powerful single agent. You don't need a million bells and whistles. Second, that length normalization thing, it's not just a clever trick. It is absolutely crucial. Without it, agents just learn bad habits. It's the key to teaching efficiency. Third, and this is so important, the agentic workflow matters. The way you structure the conversation with the model can unlock massive performance boosts even before you start training. And finally, the results speak for themselves. Their model hits state-of-the-art on a major benchmark, proving that this whole approach really works. And that leaves us with one last pretty provocative question. For the longest time, a lot of people thought that solving big, complex problems would require these giant teams of specialized AIs working together. But if a single AI apprentice can be trained to be this good, this flexible, what does that mean for the future of those multi-agent teams? Maybe, just maybe, the future isn't a factory but a workshop with a single master craftsman.